Okay. And anytime you want me to pause the recording, let me know, but please remember to remind me to restart if I pause the recording. Okay, otherwise I am recording what we're doing today. Okay, so taking a look at the schedule is the same overall schedule. All right. So remember that the homework for chapters 7 through 10, that big homework assignment, 250 points. All right. It's by far the biggest thing, 25% of the class, 250 points. Definitely want to basically get this all done, right? You may not have to finish every single problem, but definitely pretty much get it done, right? And that's all due at the end of Monday, December 14th. Also, the Alex extra credit is due at the end of Monday, December 14th. So we're going to wrap. So at your end, you're going to wrap everything up by midnight, the end of Monday, December 14th. Today, of course, is Thursday, the 10th. Although I know it's easy to lose track of days. Today, remember, is Thursday, the 10th. And this is today, right? The homework is due the end of Monday. Now, in terms of the grading, I can't predict too much about the grading, but again, today is Thursday the 10th. That's today. Okay. The last day of class is Monday the 14th. So it's quite possible that you'll have a class there. If you have a Monday, Wednesday class, for example, you may have a class meeting on Monday the 14th, maybe a final in your class Monday the 14th. And also by then, I do hope to have the chapter 4 homeworks done by then and reported back to you. Okay, the plan is for me to give you a grade report every time I finish an assignment. And then by the end of that week, I hope to get the 5-6 homeworks done by the end of that week. Now for the 7 to 10 homework and your ultimate grades, I'm looking more towards the mid-20s, December mid-20s. You may be getting a Christmas present from me. That's quite possible. Okay, so that's kind of the timeline I'm looking at. I should be all wrapped up by sometime in the mid to later 20s of December. Okay, that's kind of the timeline I'm looking at. Okay, so and if you have any questions, feel free to email me. I'll be checking both my Yahoo and SDCCD accounts. SDCCD account is better for official business like scholarship stuff, for example, right? But for homework, submit to my Yahoo account because that's unlimited storage, which I'm going to need for your homework. All right. So any questions, any general questions? Yes, and I'm hoping that it'll be a good present, right? It should be. Okay. Because, as a dictator would say, if you've been doing what I've been telling you to do, then you should be pretty much okay, right? There should be no surprises. And I do hope to give out grade reports along the way. So it won't be a huge surprise by then. You'll get a trickling of information along the way. Okay. And speaking of a trickling, I know that students may trickle out tonight, right, throughout the evening. So let me say thank you for being a great class. It's been fun working with you. Happy holidays. Let's hope for a better new year in 2021. Definitely a better new year. All right. Thank you. Thank you. All right. So I wanted to give you my happy holidays as students trickle out throughout the night. Okay. So before we are recording, gonna keep checking that we are recording. All right. Any questions before we start the usual? It's your day. It's your evening, right? Any questions before we start the string of questions, for example, in chat? Any general questions? All right.
Yeah, I have a question, Professor. Are you still going to be open for office hours before
Yes,
Monday
on
if we
Monday.
need help with anything?
Right. So email me beforehand so that we can arrange like for example like a 30-minute slot, for example. So email me over the weekend perhaps, and we can set up a time on Monday.
Okay.
Right. Yeah, that's a good idea because yeah, give me some notice. So if you would like to see me sometime on Monday, then give me an email over the weekend. Right. Even a Sunday wouldn't be out of the question. Right. But bear in mind, I will be grading the chapter 4 homeworks also. Okay, now are there any other questions before we start the list of questions? Of course, if something comes up, you can go ahead and chat at me or talk at me. All right. Any questions? Okay, so it's I have 7:12. All right. Okay, so let's go ahead and start the questions. But again, if you have other general questions, let me know in chat or speak at me. All right, so let's go through. And I may have done some of these before. Let's check. All right. In which case, I do have some notes. Okay, so 9-4, 1 and 2. All right. Oh, wait. Oh, the induction ones. Okay, now for the induction ones, I'm going to go ahead and do this. So for 941, that's the general induction one. So I might want to pause a bit on that. So I'll say this. Now I have my my planning sheet out here, the Khan Academy video. So uh, Tuesday after class, I talked with someone about induction 9.4 number 1, reiterating the induction problem. I'm going to copy this in chat. And you can either do this now or do this later on. But okay, here's the Khan Academy video on induction, which should help with 9.4 number 1. It's a reiteration of the problem I did in notes. Okay, so now I can come back to that later on, but let me go to number 2. Basically, in number 2, I wanted people to apply the formula that they saw up in number 1. So number 2, I'm asking people to use the formula from number 1. All right, so apply this formula. Okay, the handshake problem formula, right? The sum of the first n positive integers is n times the quantity n plus 1 all over 2. This is true for all positive integers n. Well, in particular, this is true for n equals 1,000. So this, what does this sum mean? It's an example of summation notation. Okay, replace the k with all the integers from 1 up to 1,000. All right, so we have 1, 2, 3, and so forth up to 1,000. And what is this operator? This is the summation operator. So this here represents 1 plus 2 plus 3 plus yada, yada, yada plus 1,000. And basically, this is an example of this over here. This is the case of this over here when n equals 1,000. The statement in 1 is true for all positive integers n. You prove that, and the Khan Academy video and my notes help show that. Number 2 is merely the example and case where n equals 1,000. So you plug in 1,000 on the right-hand side. N is 1,000 times the quantity, 1,000 plus 1. Obviously, that's 1,001, right? All over 2. All right. And the answer is, it's got a bunch of 5s in it. I know that. It's got a bunch, okay, it's in the notes here. I suspect my arithmetic's going to be kind of blown today by this time of the semester. Okay, 9.4. Number 2, 500,500. Okay, I'm sure if I tried to do it mentally, I'd miss a 0. Okay, so the sum is going to be 500,500. I think the sum of the first 100 positive integers was 5,050. I had some videos showing that. So the sum of the first 1,000 positive integers is 500,500. All right. Okay. So that's how you apply 1 to 2, and we can go back to 941 later on. Also, the Khan Academy video will sort of go over that. All right. Now there's a third question in that block here. 10.8 number 1, going up to 10.8 number 1, and I think that's a good general problem for students because we covered that on Tuesday. All right, 10.8 number 1. And I know that I did a similar problem in my notes. Okay, so let me grab my notes. Okay, I'll do this. All right. I think was it this one? It was actually this one, huh? I think I actually did do this homework problem over here. It's kind of strange I did that, right? But yeah, on number 1, I really did answer. I don't know if I realized that, but on number 1, I actually did answer the homework problem. So let's reiterate this, right? I actually do have nice notes for this. I think I meant to put a -2 there, but no, let's keep it as is. But yeah, I might want to make a note for myself that yeah, this is the same one as when I covered in class. I forgot if that was intentional or not. Okay, if I want to make a note of that. Okay, but for your class, okay, r equals 2 sine of theta, let's stick with that. It turns out I did do that in my notes here. All right, sketch the graph of the polar equation r equals 2 sine of theta, where r and theta are polar coordinates, and this is worthy of review. Okay, so I have a request. Before I forget, there's a request in chat that I show the problems so that people can take a screenshot. So this is the list of homework problems that I've covered in previous videos, whether they be at the end of the class videos, because I did them basically after class, but they're still recorded. And there are these 3 office hours I did during Thanksgiving break. So together, if you want to do a screenshot of this, these are all the problems that I've covered thus far in the videos, and you can refer back to them in the playlists. Remember that the Thanksgiving ones, I think I put them in the prior week's playlist. So check on in the playlist for class and office hours, the ones that are labeled class and office hours. Okay, so I'll give you I'll give you what, 20 seconds to do a screenshot. All right, 5, 4, 3, 2, 1. Okay, do you all have the screenshot? And remember, this isn't the video. So if you missed that, it is going to be part of the video. I am recording. Okay, and we're about, what about 12, 13 minutes into the recording? 12 to 15 minutes into the recording. Okay, so going back. So let's go ahead and review 10.8 number 1. Let's explain that again. All right. And either by luck or by mistake, I actually had the same one as in the notes. I forgot if I did that on purpose or not. Okay, but let's graph this polar equation. Now, first of all, let's graph these as Cartesian coordinates, meaning for the time being, let's pretend that r is, let's pretend that r is y and theta is like x. All right, so that theta is the horizontal axis, r is the vertical axis. All right, so this is like in chapter 4. Now this is my annotated version, right? Yeah, it's my annotated version. Okay, so here's my chapter 4. All right. Yeah, from chapter 4, how do you graph kind of like y equals 2 sine of x? All right, so it's a good morning graph, right? This is the fundamental cycle when you have sine and a is positive. Note that b is positive 1. That's good. It's positive. The amplitude is 2, and that's the only transformation. We do a vertical stretch, and the new amplitude is 2 and not 1. So the range is going from -2 to +2, okay? And here's a graph of r versus theta as Cartesian coordinates. Now remember, now here we have 4 phases. It's very straightforward. The 4 phases correspond to the 4 quadrants. In general, we change phase if we're, okay, so just in general, for your later reference, we change phase if we're changing the quadrant, if r is changing sign, like from positive to negative, or vice versa, and also if r is changing direction, like from increasing to decreasing, or vice versa. But fortunately, for this basic example, for both 1 and 2, the only time that these things happen, the only time you have these changes is at the quadrantal angles, okay, in these basic problems. In the rows problems, we have like a 2 theta or 3 theta, then that's different. Okay, now let's trace the behavior. Let's see, what would be helpful here? Okay, okay, let me duplicate this. All right, so I'm gonna go down to the answer. Right. On polar graph paper. So I have it in Cartesian graph paper and polar graph paper. These are both circles. All right. So let's go through the phases. Okay, so in phase 1, maybe I should do this in purple, green. All right. So in phase 1, as we go from theta equals 0 to theta equals pi over 2. So that's phase 1. All right. What's happening to R? R is changing from 0 up to 2. R is increasing from 0 up to 2. So when theta equals 0, R equals 0. Anytime you have R equals 0, that corresponds to the pole or origin. I'll do some green. All right. So when theta is 0, R is 0, and we get the pole or origin. And that's for theta equals 0, for example. All right. At theta equals 0, we're at the pole, R equals 0. Okay. Now, as theta increases from 0 to pi over 2, we think the particle is moving in quadrant 1. And because R is basically positive in here, R is positive in quadrant 1, yes, the particle is moving through quadrant 1. So imagine this as being the trajectory of a particle. Okay, as theta increases from 0 to pi over 2, then we're moving along this right half of the circle. And the R coordinate, which is the signed distance from the pole or origin, the distance from the pole or origin is increasing from R equals 0 up to R equals 2. Okay. And you should put that you should put that orientation arrow, right? At each phase, you should put an orientation arrow. Okay. When theta is pi over 2, R is 2, meaning that if we look along this ray corresponding to theta equals pi over 2 for non-negative values of R equals 2 is the point that's 2 units north or away from the pole over here. So that's this point up here, that north pole on the circle. That's when theta is pi over 2, and R, the distance from the pole, is 2. If R is negative, you go in the opposite direction. All right. Now, if you have any questions, go ahead and pause me in chat, okay? All right. Now, let's take a look at phase 2. I'll go through these phases. All right, phase 2. Okay, so theta is going from pi over 2 to pi. Okay, the R coordinate is decreasing from 2 down to 0. Basically, R is approaching 0. Whenever R is approaching 0, the particle is approaching the pole or origin. Okay, and it's going to trace out the left half of this circle. And again, you should put an orientation arrow every time you have a new phase. I think that's a good practice. Okay, so again, what's happening? We start with this point here, okay, at theta equals pi over 2. Okay, theta is changing from pi over 2 to pi. We think we're in quadrant 2, and because R is positive in here, we are in quadrant 2. Okay, so we go through quadrant 2, and the particle is getting closer and closer to the pole or origin. We start here 2 units off. The distance decreases until we reach the pole. All right. So for example, at this point, we're 2 units away. At this point, on this circle here, we're 1 unit away, and at the pole, R equals 0. Okay, again, anytime you have questions, feel free to pause me. It turns out that we've drawn the entire circle, and it will be a circle. Don't forget the orientation arrows, right? And it's good to put one every time you have a new phase. Now, what about from pi to 3 pi over 2? Okay, why am I claiming that we're done? Still, you want to check, right? So look at pi to 3 pi over 2. All right, what's happening there? R is changing from 0 to negative 2. Now, if theta is going from pi to 3 pi over 2, you think you're in quadrant 3, but wait a minute. R is negative in here, so you're not in quadrant 3. You're back to quadrant 1, and you're retracing your steps along the right half of the circle, okay? So when theta equals pi, R equals 0, we're at the pole, okay? Now, you might think that you're traveling along you might think that you're traveling along these guys over here, but no, you're not. Because R is negative, you're traveling through these rays over here. Okay, we start with R equals 0. R goes towards negative 2, meaning that we're approaching 2 units away from the pole, but in the opposite direction. When theta is 3 pi over 2, you might think you're south of the pole, but no, because R equals negative 2, you're not south of the pole, you're north of the pole. Again, you're 2 units north of the pole, you're back to this north pole point on the circle. Likewise, as theta goes from 3 pi over 2 to 2 pi, you might think you're in quadrant 4, but no, because R is negative, you're not in quadrant 4, you're in quadrant 2. and you're retracing the left half of the circle, r is going from -2 to 0. It's moving towards the pole. R is moving from this point, that's 2 units north of the pole, 2 units away, 1.5 units away, 1 unit away, half unit away, and then you reach the pole when theta is 2 pi. So you reach the pole when theta is 0, when theta is pi, when theta is 2 pi, and in fact for any integer multiple of pi. Theta equals 0, theta equals pi over 2, theta equals pi, theta equals 3 pi over 2, but r is -2, so you go north of the pole, and then theta equals 2 pi back to the origin or pole. All right. Are there any questions about that trace out? Okay, now I can come back to this later on. Okay, again, 941, I can go back to if need be, but remember, I have the Khan Academy video if that helps out. It's also in my playlist. Okay, so let's go on to 9.3, number 9. Ah, yes, okay. A very common one. Okay, and before I forget, I'll go ahead and put this. I may want to save this for later, so I'm going to put this on the on my scratch sheet here. I could do it right here, but I want to save this. Okay, so this is 9.1, number 9 of PDF. All right. Okay. So for what values of x does this series converge? First observation, what kind of series is this? So if you wanted to write out the first few terms of this thing, right? Summation n equals 1 to infinity, 3x all to the n. All right, when n equals 1, we get 3x. This means summation. When n equals 2, we get 3x all squared. Plus, when n equals 3, we get 3x all cubed. You didn't have to write this, okay? This is an infinite series, infinitely many terms, n goes towards infinity. Now, what kind of series is this? For any real value of x, let's say non-zero for now, but I don't even exclude that case, really, okay? We're moving from, as we move from term to term, all right? As we go from here to here, here to here, and so forth, what do we keep multiplying by? There is a common ratio. 3x times itself is the square of 3x. 3x times this is the cube of 3x, and so forth. There's a common ratio. It's 3x. To get to each new term, you multiply by 3x, another copy of 3x. Notice I said common ratio. What do you call a series where you have a common ratio between the terms? That's called a what? What kind of series? That's called a geometric series. Okay, it's called a geometric series because the terms form a geometric sequence. 3x, its square, its cube, its fourth power, and so forth. A geometric sequence and a geometric series, by definition, have terms that have a common ratio like this. Here, 3x. But now we want to know, when does this geometric series converge? We know it's a geometric series. And sometimes I'd exclude the case x equals 0. Let's not worry about that for right now. For right now, let's say x equals 0 is fine, actually. All right. So we have here a geometric series, even if x equals 0. We have a geometric series. For what real values of x will this geometric series converge? Well, what is the convergence condition for a geometric series? All right. A geometric series converges, meaning it has a sum. If and only if, remember, by definition, a geometric series has a what? A common what? By definition, a geometric series has a common ratio, R. Now, when does a geometric series converge? Well, remember if the base here, if the thing that we're squaring, cubing, and so forth, if the base here were like 1/2 or 1/3 or 0.1 or negative 0.1, the series will converge. So basically, it's if R is strictly between -1 and +1. That was the condition for the geometric series converging. By the way, that's also the condition for the terms themselves approaching 0. Now, a simpler way of writing this, a lot of books write this as the absolute value of R is less than 1. That's the exact same condition, right? The solution set for the absolute value of R is less than 1 is basically this, the set of all real values of R, where R is strictly between -1 and 1. A lot of calculus books write it like this. Okay. Now, actually here, this form is actually easier for us to use right now. So again, when does this geometric series converge? When R is strictly between -1 and 1. What's R here? R is 3x. When 3x, so this series in particular will converge. This series in particular will converge, okay, converge if and only if, if and only if 3x is strictly between -1 and +1. We have here a compound inequality. It's okay for us to divide all three parts by 3. We want to isolate x. You can divide all three parts by 3. By the way, if you divide by a negative number, you have to flip the symbols. But of course, 3 is a positive number. We do not flip the symbols. So to have convergence, that happens if and only if x is strictly between -1/3 and +1/3. Okay, so I think I put that in interval form. The corresponding interval form, okay, is the open interval from -1/3 to +1/3. So this series, this infinite geometric series converges if and only if x is in this interval over here. Because if x is in this open interval, then 3x is in the interval from -1 to 1. I'll put that in red. If x is in this purple interval, then that means that 3x is in the interval from the open interval from -1 to +1, which is the exact condition for convergence of this infinite geometric series. A lot of good ideas here. And folks, this is a routine calculation in Calculus 2. That's a very common thing to do. You're often asked in a Calculus 2 class, Math 151, for which real values of x does this infinite geometric series converge? This is the kind of thing you do. You will see this if you're STEM.
Oh, by the way, Professor, that's 9.3. You put 9.1.
Wait, let me see here. Oh, right. So I'm answering the correct student's question. I said I made a mistake.
Yeah, no. I'm just telling you, you put your file wrong. You put it as 9.1.
Where did I write 9.1? Where did I write it?
Like when you name the file so that you can look.
Oh, and
back
I named
at
the
it
file.
later.
Thank you. Oh no, thank you very much. That'll help me. So thank you. That helps me. All right. Okay, thank you very much. Yes, that'll save me some heartache. Quite a bit of heartache, actually. Thank you very much. Okay, yes, that's 9.3, number 9, because 9.3 we dealt specifically with geometric series, especially infinite ones. Thank you. 9.3, number 9, right. And I'm glad I answered the student's question. If I hadn't done that, I would have felt really bad. But in any case, I should have answered this anyway, right? Whether it was asked or not. Okay, now, are there any questions about this? This is a good problem. And remember, I often like to grade problems I cover in video, right? Questions about this. It's a good problem. Preview of your Calc 2 class. Okay, I'll save this. I'm glad I'm labeling it right now. Thank you. I'll save that. Okay. 8.48. All right, that sounds like determinants. Okay. I'll go ahead and click off on this. I can click off on these for now. All right. Let's try 8.4, number 8. All right, that's determinants. Okay, remember, what were the optional sections? I'm gonna put this in the what? I should have done this early on, actually. Okay, the optional sections, the ones that you don't have to do, 8.3, 8.5, 10.4. And I did email about this. So some students might be going, oh, darn, I did it. But these are ones that are not required for homework. Okay, they're good for your education, right? And before you take linear algebra, maybe do these, right? But 8.3 was on inverse matrices. 8.5 was on applications of determinants, like to geometry and Kramer's rule. 10.4 was on harder hyperbola problems. So these were all optional. Still, they're good for you, and I do encourage you to look at these someday. All right, but so 8.5 was optional. 8.4 was required. Okay, so you're not wasting your time on 8.4. Ah, yes, a popular or unpopular one, as the case may be. And I know I've worked with this with students before. I don't think I've done this in a video though. I've emailed about this, but I haven't done this in a video yet. So let me go ahead and do this. It's good for me to do this from scratch, actually. All right, so oops. Okay, and let me title it right first of all. This is 8.4. Yes. And feel free to shout out if I make a mistake again, right? Save this. Okay. 848. Okay. Get this right. 8.4, number 8. All right. Good one for us to look at. All right. Now, okay, so I don't want to be triggering. Let's use like purple. Okay. All right. Now, my recommendation to the student was that you could let x be lambda. Okay. Because right off the bat, some of you might be creeped out just by that notation alone. All right. So actually, I'm going to go ahead and do that. Let's let x be lambda because remember, the answer to a solve an equation problem is a solution set. So your final answer doesn't even have to include the letter x in it or lambda, right? So I may as well say let x equal lambda, and let's do this with x, and that makes you feel better. That in of itself might save you. I'll recopy the problem. So again, it's 8.4 number 8. Okay, I'll recopy it. Solve the following equation for lambda or now x. Actually, I'm going to solve this for x now. So I'll rewrite the problem with x. Okay. Of course, if you use lambda, great. But I think for some students, it might help if we use x. All right, solve this equation. It turns out that the value of this determinant is a polynomial in x. How do you take the determinant of a 2 by 2? All right, so it's a butterfly. It's AD minus BC, right? It's the product along the main diagonal. Quantity 4 minus x times quantity 1 minus x. Again, if you have lambdas, great. It might be good practice for you to write that. But again, I think some students might have been confused by that alone. Minus the product along the skew diagonal, -2 times 1 is -2. We're subtracting -2. A lot of people mess up the sign here. Equals 0. All right. This turns out to be a polynomial in x. FOIL this part here. Distribute. It's your usual algebra. Again, if you use x, that might be more clear. 4 times 1 is 4. 4 times -1x is -4x. -1x times 1 is -1x. -1x times -1x is a positive 1x squared. And don't forget the plus 2. I almost forget that because we've worked out the determinant. Don't forget there's also a plus 2 here. Okay, that's from minus the product along the skew diagonal. Don't forget this guy here. Equals 0. Now, at this point, I think a lot of you will be able to get it from here. You should be able to get it from here because you're basically solving a quadratic equation in x. But while we're at it, I may as well finish this, right? And I'll tell you the motivation. Okay, let's put this in descending powers. We have an x squared term and x term. Let's put this in descending powers. So we have an x squared. -4x minus 1x is -5x. Positive 4 plus 2 is positive 6. And yes, the quadratic formula, the QF works, but I hope you can factor this old school. Factoring over the integers. Alex can help you. I mean, seriously, some of you could use the Alex review just for your own education on factoring. Okay, so x and x, teacher's nice. We have, this does factor over the integers. Okay, same signs, both minuses. 2 and 3 or vice versa. Here, the order didn't matter, right? All right, check it. Negative 3x minus 2x is negative 5x. The solutions are x equals 2 or x equals 3. By the zero factor property, you set each equal to 0. But at this point, I'm okay with you skipping that step. You can go ahead and go straight from here to here, right? If you have this equals 0, I'll believe you if you say x equals 2 or x equals 3. Technically, it's an or there. Okay, for this to be true, x could be 2 or x equals 3. But remember, your answer to a solve an equation problem, whether it's this in x or this in lambda, is a solution set. So your final answer is a solution set. Solutions in a solution set are unordered, but it seems natural to put the 2 first. If you switch these, that's fine. Okay, that's really your final answer. And notice here that in your final answer, you don't even have to write x or lambda. So it didn't even matter if you did this basic substitution or not. Bottom line, 2 and 3 are the values for the unknown, the variable here, that will solve this equation, either this one in x or this one in lambda. And in case you're wondering what the motivation is, these values for x or lambda, these are called eigenvalues. Okay, these are called eigenvalues for this nice matrix over here. And eigenvalues are really key in engineering, and that's a critical topic in Math 254, linear algebra. So I'm giving you a preview of Math 254, linear algebra, which basically all of chapter 8 was. All right, I'll put the, again, this will be in the video, but again, here's the solution. If you want to say let x equal lambda, play with x, be my guest, your final answer is a solution set, and it doesn't even involve x or lambda. I mean, you can just put these numbers with the braces, comma, and you're good. That's a solution set. That's the answer. Now, obviously, if I grade this one, and I may well, if I grade this one, I want to see the work. So don't just give me the solution set. I gave you that online. Give me this work. You can substitute or not substitute, but show me basically this work. I want to see basically all that algebra. Okay, so I do want to see all this, whether you use x or lambda. I want you to basically show all of this, including the foiling. Please show your algebra. Remember, I'm giving you the short answers in my online answer sheets, right? So I'm grading your work. I'm grading your work. I might grade some short answers here and there, for example, but I'm sure I'm going to grade some problems where I'm actually grading your work, unless I feel super lazy or stressed. I hope that's not the case. All right, I do plan on grading some work, which we're doing like now. That's a good problem. That's a great problem to cover. I knew I was going to cover it. I knew I was going to cover it, and it's my pleasure. Any follow-ups on that? Any follow-ups? I used to love putting this on final exams, so I could well grade this one. All right, we can always come back to this. Save it. All right, again, induction, I can come back to 941 later, but in the meantime, if you want to watch the Khan Academy video, that's fine. Please remember to mute. I've muted you, but yeah, all right. All right. Okay, so we're looking back at 9.1, right? Okay, 9.1, numbers 8, C, and D. Oh yeah, yeah, I knew I was going to do these too. Factorial simplification. I know these ones. Yeah, I was expecting to do these. Yeah. If not, I would have done it voluntarily, right? Okay, so I believe in a previous video, actually, I did the 8B in a video, I think. Let me look here. Yes, it was my first problem after class on Tuesday. Well, it was technically in class, but it was the first problem that students asked of me after I showed my videos. So that was the first problem in my Tuesday after video portion of the class, and it's in my Tuesday class video for this week. So 9.1 number 8B I cover then. Okay. Okay, that was the easier case. So if you're really confused by these, you might want to look at the easier case. Well, let's do C and D now. I knew I was going to do these. All right, and I'm going to need a scratch sheet. Definitely. All right. All right. So this is 9-1. Right. Remember, in section 9.1, I was assuming that you hadn't seen arithmetic or geometric series yet. I know that in number was it 17? In number 17, some people use the formulas from arithmetic or geometric. Now, I'm not going to mark you down for that. Frankly, I'll accept answer only for these, but I want you to figure them out too. The idea was for you to kind of get these from scratch without the later formulas, but obviously on the homework, I won't mark you down. Okay. But the idea was that you should try to do these from scratch. Maybe that comment was too late, but all right. But anyway, let's go back to 8C over here. 9.1, number 8C. Okay, B was covered in the video. Frankly, I should probably play that actually, but okay. You know what? No, I was going to replay the video. No, you can go ahead and watch that on your own. Let's try to do it from scratch on C. And if you get confused, you can refer back to this video, and you'll have this video to go back for these. Okay, so let's go green. Go green, environmental. Okay, we're going to simplify this expression. And again, folks, you will see this in your Calculus 2 class, Math 151. These are routine operations with factorials. But when I talk Calc 2, even good students had trouble with these. They forgot that stuff or never learned it. Okay, so let's simplify that. All right. So this is 9.1 8C. All right. Okay, we're going to simplify this expression. N minus 1 all factorial over n plus 1 all factorial. Now, a tip that I mentioned for both A and B before, especially A actually, over here, which I mentioned very briefly, plugging in a basic value for n, like n equals 2 or 3, might be helpful. Now, that's not a waste of time, but I'm not going to do that here. But as a way of orienting yourself, you might want to consider plugging in a nice integer, like 2 or 3, for example, to get a flavor of what's going on. But let's dispense with that for now. Let's try to do this directly. Now, I do want to see some work here, by the way. I don't want to see answer only. I do want to see some work here, all right? So what's an example of some work? All right, first of all, assuming that n is a positive integer, right? At least 2, all right? Which is the greater factorial? Which represents a greater quantity? Is it the top or the bottom? It's going to be the bottom, all right? For these kinds of values for n, positive integer, at least 2, the bottom factorial is going to be bigger. N plus 1 all factorial will be a greater quantity than n minus 1 all factorial. All right, so what am I going to do? We are going to start expanding. We are going to start expanding this factorial. By the way, those of you who use Macs, this icon over here is for like lines. This one over here is for freehand. All right. Okay, I'm using preview on Mac. Okay, so we're going to expand that bottom factorial. All right. Well, how do we do factorials? Let's go back to the basics. What's 4 factorial? An algebra 2T, algebra student asks you, what is 4 factorial? What do you say? Using the countdown method, it's 4 times 3 times 2 times 1. It's the product of the integers from this here down to 1. Likewise, over here, assume this is a fairly big integer. We start with n plus 1, kind of like the 4 here. Okay, so it's kind of like, this is a case where n equals 3, and we're dealing with 4 factorial, all right? But then what's next? Here, 4 minus 1 is 3. That's the countdown. What's n plus 1 minus 1? Going from here to here, what's n plus 1 minus 1? What's 1 less than n plus 1? Well, it's just plain old n. Now who's next? When you take 1 away from n, who's next? It's the quantity n minus 1. Kind of like the 2 here, right? So it's like we start with 4, then we have 3, then we have 2, right? We start with n plus 1, then we have n, now we have n minus 1. Now, without wasting your time and money, again, what's the deal? You multiply down to 1. So this were 10 factorial, right? It's like this thing would be like 10 times 9 times 8, yada, 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 times 1. Okay, this is a yada, yada, yada. That's 8 factorial. I kind of gave it away there, right? What is this product from n minus 1 all the way down to 1? That is n minus 1 all factorial. Why am I doing that? Because it matches the top. And n could be like 10 or 100 or a million. These could be really ugly factorials. Doesn't matter because what happens? Bye-bye. They divide out. We assume they're not 0, right? They divide out. Okay. Of course, you don't have to show this work here, but I do encourage you to show this work here. In fact, let's say that I'm requiring you to show this work over here, basically. All right. I am requiring work on this one. Okay, so, okay, now this is a side note over here. So what's your final answer? I'll put this in blue. What's your final answer? Equals? Let's see. Down here we have n plus 1 and n, right? Okay, and these guys cancel out. Hey, folks, is this my final answer? Is that my final answer? Hey, look over here. We have n plus 1. We have n. Those are survivors. These guys got canceled out. Is that my final answer? Is that my final answer? Some students might say, oh, well, you can put the n in front. True, true. Is that my final answer? You can probably guess the answer is no, right? What's wrong? What's wrong? Oh, now, yeah. Now, again, true. This does expand out to n squared plus n. True. Yeah. 1 over. Thank you. I cannot tell you how often students make that mistake. It's wishful thinking. We hate fractions so much, we forget there's still a 1 up there. See, this is one reason why when you do this kind of cancellation, this kind of top-down cancellation, if you're wondering, how come he's putting 1 all the place? Because a lot of people forget there's a 1 up there. You have a survivor up on top, up on the rooftop. You have that 1 up there. Don't forget him, okay? It's a fraction. It's the fraction 1 over, and you can write this bottom in various ways, like this. You can put the n in front. I don't care if you distribute. But basically, you need something like these guys. Well, 1 over, right? 1 over. So any of these forms, I'll accept any of these 3 forms, but do show the work here. Show work. Okay, I won't accept answer only. I gave you the answer, right? Show work. Okay, I'm not impressed by the answer only. I gave you the answer. All right, show me the work. Right. Yes, common error. Folks, and this happens with me too. We hate fractions so much, we want to avoid them psychologically. That's one reason, that's one serious reason why whenever you do a top-down cancellation, put 1s. Or if there's a switch involved, put a -1. But put like a 1, okay? Because we often forget that 1 up there. We forget it's a fraction. That's an extremely common error, okay? Questions. I'll leave this up here. You might want to do a screenshot. It's in the video, but the screenshot can still help you. Like on preview, if you want to do a screenshot, preview file, take screenshot. If you choose from selection, you gotta choose the selection thing. Yeah, the selection window. All right. While we're at it, let's do D. Well, why don't we do this here? And remind me to come back to this. Okay, 9.18D. I'm going to put this in myself. Folks, based on these principles, if you know how to do the next problem, whatever it is, why don't you try D? So I've shown you C. B is in the video. A is basically the recursive definition for factorial. Try D. As an exercise for you, try D. Ask yourself, which is the bigger factorial? Expand it out, and then try to do appropriate cancellations. Remind me to come back to D, but in the meantime, let me go ahead and switch over to the next one. So those of you watching the video, you can fast forward if you need to, but, or click ahead with YouTube. But oh, you know what I'm going to do? Just so I don't forget, I'll come back to this. I'm going to pick up a new. window, and I'm gonna save it as, because I'll do it. Oh, by the way, don't distribute. When you work it out, don't distribute. It'll be a pain. We're safe. Here it is. Yeah. All right. So in due time, I'll do 918D. All right, but let's put it on the side for now. I want you to work on it. Work on this for now, okay? 3n minus 2 all factorial over 3n plus 3 all factorial. Try that out based on these principles. In the meantime, let me check chat. Let me do the next one at least. Right. Yeah, that's a cute comment in chat. That's true. -2 sine of theta was in my homework notes. So at least, my homework is a good check to see if you've been watching your notes. So kudos to the students who have observed that. Have you been reading the notes or watching the video? So yeah, I mean, why not reward those students? Maybe I did it on purpose. I think I did that on purpose, maybe. 10.8 number 1. Okay. Uh, let's see. Okay, so is that an ellipse one? Okay. Okay. Yeah, I can do an ellipse one and then come back to this. So these are some big ones, um, which I could grade, right? They'd be pretty expensive. Hey, folks, it's a 250-point final, so it's going to take me time. I'm probably going to grade a fair number of these. It's a 250-point final, which will take me some time. That's why it might take me till could be the 28th even, but yeah, the final's going to take some time to grade because I could grade a lot of these high value problems. Okay, so let's do an ellipse one. Then remind me to come back to D, right, on this here. But I'm going to grab another whiteboard. Let's do ellipses. Lots of good work here. Yeah, I'm going to give up the ghost. I won't be able to stay on the screen. So we're doing an ellipse problem, right? So 10-3. Now, I just had one problem though, right? Or two. I had two. Yeah. But the chat question was for 1. Okay, so the chat question was for 1C and 1D. But you know what? Because I know students are going to ask about this, I'm going to go ahead and do A and B. All right, why not? So I'll do A, B. I'll do 1. Okay. All right. I'll do 10.3 number 1. Okay, and then I'll leave 2 for you for the time being. All right, but let's do 10.3 number 1. That sounds fair. All right. I never get used to where things are. All right, so technology. Okay, so this one is 10.31. I'm gonna do the whole thing, right? 10.3 number 1. Let's do the whole thing. It's worthwhile. Yes, I could well grade. In fact, it's very likely I'm going to grade an ellipse problem, although it could be 1 or 2, right? All right. So I could grade 1, or at least you'll need the skills from 1 on 2. 2 is a lot like 1, right? Okay. Although 1 might be horizontal, 1 might be vertical, right? Okay, so this is going to be 10.3. Oh, what color is this? Yeah, okay, that's like a dark, like a purple, blue purple, right? That's a good color. All right. All right, 10.3, number 1. Let's do a full-blown ellipse problem. 2, I'll leave for you for the time being. Then we can come back to this. So folks, hey, if you're up for it, I'll be up until 10:30 p.m. So hey, if you're up for it, and I'll put the video up, you'll have like 3.5 hours of good stuff. You can fast forward. Click ahead. All right, this one here. Okay. So that's that. I won't recopy it, okay? But I will group the X stuff and the Y stuff. So first of all, let's group. On the homework, you don't have to recopy, but for your reference, right, as a student, you may want to. Okay, but let's group the X stuff and the Y stuff. Let's group the X stuff. You have the group 4x squared minus 24x plus, in a hyperbola problem, you'll have a minus, but still, it's a plus. And I know I didn't assign hyperbola problems, but on this. Okay, on this chapter. Now on this here, we have the Y stuff. What, 25y squared? Plus 200y. Okay, now the 336, I don't want the non-zero constant here. I want a non-zero constant here. Don't say move. say subtract. We are subtracting 336 from both sides. We have a negative 336 over here. I know a lot of algebra teachers say move. I don't like the word move because a lot of people mess up their sign. You're subtracting 336 from both sides, okay? Feel free to interject if you want me to pause or if you have a question, right? But we're grouping the x stuff and the y stuff, and we have our non-zero constant on the right side. There's a sign flip. All right, next step is to factor out the leading coefficients. I should have typed it. Well. All right. So the leading coefficient here was 4. I don't care if that's a negative 23. Okay, you can get a fraction, but here it turns out we won't get fractions. You always factor out the leading coefficient. I don't care if that leaves a fraction there. Well, I'll care, but it doesn't matter. You got to do it anyway. All right. 4 factors out. When you factor, you divide. X squared minus 6x. I'll leave a blank there for obvious reasons. Plus, I hope, plus factor out the 25. Y squared plus 8y. You use a calculator. Space there equals negative 336. Now I was being a tiny bit lazy here because I didn't want to rewrite this because because on the same row I'm going to do the following. I'll put this in red. I'm going to complete the square. All right, complete the square. Okay, half of negative 6. Well, the sign at this point doesn't matter, but half of negative 6 is negative 3. And the square of negative 3 is positive 9. Okay, the negative 3 does help later on. Okay, that's one advantage of keeping the sign for later on. Now over here, okay, the leading coefficient right now is a 1 inside the parentheses, right? Because we factored out the 25. 8. Half of 8 is 4. The square of 4 is 16. It's always a plus here, right? Plus 16. Okay, half of 8 is 4. Square of 4 is 16. And what else do we have to do? I mentioned that we had to CTS, but what else do we have to do? And we have to balance. It's like compensating or balancing. We have to CTS and balance. Okay, I put a plus 9 here. I put a plus 16 here. So I'm going to have to put stuff here, right? Let's say a student does this. What do you think? I ask a student or a 2T, okay, so you put in the plus 9 here and the plus 16 here. What do you think? Well, you have to do some sort of balancing, right? Have we balanced it? No, we haven't. What's the issue? Why is this not balanced? What numbers are preventing us from balancing here?
They're being multiplied as well.
Exactly. The leading coefficients, the 4 and the 25. Because here's the thing. When you insert the plus 9, the 4 eventually distributes to the plus 9. So when you insert a plus 9, you're not adding 9. You're adding 4 times 9 or 36. You can put 36 here, but you're adding 4 times 9 or 36. Likewise, when you insert the plus 16, you're not just adding 16 to the left side, you're adding 25 times 16 by the distributive property. So you're adding 25 times 16 over here. Okay. You know, I was trying to think, what is that? Think of it this way. 4 quarters is $1, right? 16 quarters is $4. That's 400. I used to have a hard time multiplying those, but think in terms of quarters and dollars. That's 400. Think in terms of quarters. That's 400. That's 36. 436 minus 336 is 100. My arithmetic is horrible in real time, but even I could do that. That's 100. And I knew I was being nice. I knew that this was going to be a nice perfect square. It didn't have to be. In Calc 2, that could easily be a 99 or a 101. But the fact it's 100, I knew I was trying to be nice here. All right. So the next step. Very good. Next step is to, okay, now these are now PSTs, perfect square trinomials. We're going to do more factoring. We're going to factor the PSTs. And simplify, obviously. Simplify that, obviously. That goes without saying. All right, over here. 4 times the square of what? A PST is the square of a binomial. X. And this is where this guy comes in handy. Remember, -3 was half of -6 when we completed the square. This is the guy that goes here. That's the bottom line. All right. This is the square of x minus 3. Okay. Another way to look at it, the square of what is 9? Both 3 and -3, but since this was negative, it's the minus sign. But it's easier to pick up this halfway guy. All right. Plus 25 times the square of what? Times the square of y plus 4. Right there. Y plus 4. Okay. Observe the square of 4 is 16. We'll have a plus sign here. All right. Equals. Okay, even I could do the arithmetic mentally by using some tricks here. 16 quarters is $4, 400 cents, plus 36, that's 436. Subtract 336, that's 100. And remember, we're basically adding 3 terms here, so that's commutative. Okay, here we're adding a negative 336, so I could do these in any order. All right, that's good. That's very good. But we're still one step away, basically, from standard form. All right, so now we got to write down the standard form. Purple? Okay, yeah, standard form. All right. We need a 1 here. Okay, kind of like with matrices, fast, dirty way to do it, divide all the terms by 100. In fact, I'm going to show that. Now, you don't have to show this step, but I will show you this step. This term is divided by, okay, I'll do this. Let's recopy these. And we're going to use, and we're going to divide all 3 of these terms by 100. Oops. And then I'll use this icon, okay, for straight line. There we go. My fraction bars stink. There we go. Good. All right. So you learn at the end. A great quote from the philosopher Ozzy Osbourne and musician. You don't know, what did he say? He said, by the time you have it all figured out, you die. By the time I have it all figured out, I'm done with the class. All right. Good life lesson there. Okay, now here's the thing. If we had like 99 or 101, we want to form compound fractions. Okay, so here's what I'm saying. X minus 3 all squared over. Now, here's the thing. If you're multiplying by 4 over 100, you're dividing by 100 over 4. And in fact, if we had a 99 there, you would write this as 99 over 4, okay? But of course, we don't have to mess with that because straight cancellation works, right? Or straight division. 4 divided by 4 is 1. 100 divided by 4 is 25. So I didn't have to go through all this mess here, but this is what I would recommend if you had like a 99 or a 101 there, right? Then you would need fractions down there. Here we didn't need fractions down there. We don't need a compound fraction. We have a straight up 25. Oh, plus sign, right? Plus sign, all right. Y plus 4 all squared. Okay. Again, when we do our cancellations or divisions, 25 divided by 25 is 1. 100 divided by 25 is 4. Or if you multiply by 25 over 100, you're dividing by 100 over 25. You're dividing by 4. Either way, you're dividing by 4. Over here, we have a 1. I'll put in my nice fraction bars. Or the computer's nice fraction bars. There you go. That's standard form. That's part A. Show your work. Whoops. Show your work. Show your work. Show your work. Now, you don't have to put the commentary. The commentary may be for your benefit. So as a student, you might want to write this down just so that as you assemble your notebook, right? I hope you're keeping a notebook for this class. These are good notes for you, okay? But basically, I want to see this algebra, right? Including the balancing and all that. I gave you the answer. Don't give me answer only, obviously. And I may well grade one of these for credit. including the partial credits. And that is the answer, right, for A. And the student wasn't even asking about A, but I needed A. May as well do it. Yeah, okay, so we have x minus 3 all squared over 25 plus y plus 4 all squared over 4 equals 1. That's a nice typeset there. Don't forget the equals 1, all right? Okay, any question about A? I know the student was asking about C and D, but I needed A first. Let's do the others. Okay, other parts. Okay, and after this, we'll take a break. All right. So I'm asking for what? Okay, so here's the standard form. I'm going to move this around. All right, hold on, 1 second. So once we get standard form, I don't erase your work, obviously, but I'm going to focus on this standard form here. All right. All right. And that should be good for us from now on. B, find the center. Okay, so by the way, this is a see 10 1 number 1 part 2. Yeah, okay. Dot PDF. Okay. All right, find the center. Did I mention this was A? This is A. This is A. All right, this is B. The center. Key tip. I mentioned this before for circles in chapter 0. What makes the left side of the standard form equal to 0? That's a nice tip. X equals 3, y equals -4. Remember, the general form is x minus h all squared over, in this case, a squared is the bigger number, 25, over here, plus y minus k all squared, whoops, over b squared equals 1. And the center is h comma k. All right. X minus 3, h is 3, y minus -4, k is -4. Okay. What makes the left side equal to 0? C, finally, let's answer the poor students' questions. All right. The vertices. Oh, no, yeah. This is where a basic sketch will help. All right. Yeah, okay. So here, I think I'll go to Desmos, but I'll do C here. All right. I'm going to switch over to blue. Okay, let's do C in blue. All right, what's the deal? What's the deal? Let's go to a light blue. Okay, what's the deal? Now, the bigger number is under the X stuff, so it's a horizontal ellipse. It's a horizontal ellipse. Because one moment. There we go. Because this here is the bigger denominator. It's the larger denominator. Therefore, horizontal ellipse. That's big. That's key. Okay, so we have a horizontal ellipse, remember. All right. I'll do just a basic sketch here. Horizontal ellipse. The center is here at 3, -4. Okay, now where are the vertices? Over here, I'll call this V. Over here, I'll call this V prime. Okay, now I want to know the coordinates of the two vertices. Now, they lie on the same horizontal line. Which coordinates stay the same? When you look at this street here, the major axis, when you look at the major axis here, I should. When you look at that major axis, what stays the same? The x coordinate or the y coordinate? Which coordinate stays the same along this major axis? What stays the same for the center and the two vertices? It is the y coordinate. This is part of the line y equals -4. -4 is the same y coordinate. But the x-coordinate changes, okay? The x-coordinate changes. By how much? By a. What's a? Ah, good question. A squared is the bigger denominator, 25. A squared is 25. Therefore, what's a? Well, first of all, algebraically, a is plus or minus 5, but by definition, a is positive. So a is just positive 5. A is positive 5 meters, I guess, or whatever. 3 minus 5 is negative 2. 3 plus 5 is 8. These are the vertices. Okay, and it's okay if you just box these in. All right, and there's other vertices, right? Negative 2 comma negative 4, 8 comma negative 4. Very good. All right. Any questions about how to get the vertices? A key question is, compared to the center, what's staying the same and what's changing? And this is kind of like what we did in trig with amplitude, except here we're changing the x-coordinates, right? We have 3 minus 5 and 3 plus 5. Any questions thus far? All right. And I didn't care so much about the minor axis. That's for B. Now, B does come up for the foci. I'll do this in green. They'll do this in Desmos, and we'll take a 10-minute break. All right. But you can still put questions in chat. So feel free to go ahead. I'm going to keep the chat on, obviously. So during the 10-minute break, feel free to put more questions in chat. All right. Let's go to green. All right. Over here. D. Same. Whoops. Let's go to green. Same principles as before. But first of all, we have to do something. We have to find C first. Do we have room? Yeah. We have to find C first. Careful. C squared equals A squared. Careful. It's minus B squared. Remember, A is the distance between the center and either vertex. C is the distance between the center and either focus. A is bigger than C. C is less than A. C squared is A squared minus B squared. C squared equals, all right, well, A squared is 25. Note, B squared is the other denominator, 4. B equals, we start with plus or minus 2, but B is positive. B is 2. Right. All right. So we have, and in fact, we didn't have to find B. I mean, we just needed B squared, really, right? So A squared was 25. We didn't even need B per se. 2 is the distance from here to that point and that point. But we don't care as much. B squared is 4. 25 minus 4, that's 21. If C squared is 21, don't forget, C equals, we don't need the plus minus, it turns out, the square root of 21. All right, that's simplified. All right, which means when I go back to the ellipse here, oh, it's horrible. Okay, I get no points for artwork. Okay, now, again, we have this street, okay, the major axis, because all 5 of these key points, whether it's the center, the vertices, or the foci, all 5 of those key points lie on the major axis. The center, once again, come on, is 3, negative 4, once again. The center, the center didn't change. All right. Okay, now for the foci, I'll put those in green. Now, I don't know where they are exactly. I'm just sketching it out, right? We'll find out on Desmos later on. But the foci will also be, it's kind of elongated. So I think it's going to be kind of, well, the way I drew it is elongated. Well, A is 5, B is 2. Yeah. Oh. All right. Here's C. Distance from the center to either focus. All right. So for the foci, F and F prime. Same principles as before. What stays the same? Just like for the vertices in the center, the y-coordinate stays the same. The y-coordinate is -4 for all 5 of these magical points, the center, the vertices, and the foci. But the x-coordinate changes. We start with 3, and here we're going to do it very explicitly, right? Kind of like over here. Right? For this focus here on the left, we subtract c. It's 3 minus root 21. I'll box that in. For this x-coordinate, it's 3 plus the root 21. If you wish, you can approximate that. I hope that's the answer. Yep. The foci go 3 minus root 21 comma -4 and 3 plus root 21 comma -4. I'll save this. I'll give you a few moments to write this down. While you do that, I'm going to pull up Desmos. And I will go back to that screen. Okay, so I'm going to go back here and I'll go to Desmos. I'm going to graph the ellipse. All right. Here's the ellipse in its full glory on Desmos. Nice. Okay, not my scratchy ellipses. That is the ellipse in its full glory. X-axis here, y-axis here. Just like with trig functions, I'd probably put the axes last after I got all these coordinates right. Okay, and we're saying the center is at 3, -4, right? We're saying the center is at 3, -4, right there. Looks good. The vertices are at -2, comma -4. That looks good. And at 8, comma -4. And that looks good. Okay. What else? Should I go to projector mode? That helps to. Yeah. All right. And then the foci over here, the foci. 3 minus square root 21, all -4, comma -4. Oh yeah, it's very elongated. Yeah. So the foci are very close to the vertices actually. As a student, you know where they are, but you don't know what makes sense, right? For the foci, 3 plus root 21, -4. But the math works out. Yeah, it turns out the foci are actually very, very close to the vertices, and this is a very eccentric ellipse. That's part E, by the way, right? Yeah, what's the eccentricity? In brown. What's the eccentricity? In brown. All right. So in E is about E. That's convenient. E is about E. Part E is about eccentricity E. Whoops. All right. Part E, which is about E. There's a formula. E equals C over A. C is root 21. A is what? 5? Root 21 over 5. As a number, as a decimal number, that's about, Desmos will say. It's a calculator too. Square root of 21 over 5. Yeah, look at that. It's about 0.917. Yeah, that's very eccentric. Remember, the eccentricity E for an ellipse is a number strictly between 0 and 1. 0.917 is very eccentric. It's very elongated. Okay, so this is very elongated. The coordinate axes are scaled the same because you have to have equal scaling on the axes to get a good sense of how elongated something is. So yeah, this is an eccentricity of about 0.9, and the foci are very close to the vertices. It's very elongated. All right, about 0.917. And that should answer all of number 1. Find standard form. That was the equation, right? We found the center, and then the vertices, then the foci, and the eccentricity, which is a number. Did I forget anything? Oh yeah, I was going to mention that geometrically, that means that the distance from the center to either focus is about 92%, is about 92% of the distance between the center and either vertex. So that indicates strong elongation. Question in chat. Can the eccentricity of the ellipse be found by the angle of the intersecting plane? Interesting question. And that's true. That is true, because for an eccentricity of 0, that's when the plane, you're talking about cross sections, right? I go to that video. So this is what the student's talking about. It was a private question, but so you have a cone, right? Okay. Now, if the plane is intersecting the cone perpendicular to the axis, then you're going to get a circle as your cross section. But if the plane is tilted, then you're going to get an ellipse. And the more tilted the plane is, the more elongated and eccentric the ellipse will be. So there will be a relationship. So there may be a formula. I'm sure there is some sort of formula about that. I don't know it off the top of my head, but that's a good observation, that the eccentricity of the ellipse is a function of the angle of the intersecting plane. That's a very interesting geometric question. I don't have the formula off the top of my head, but yeah, I'm sure that there is a formula about that, right? Okay, any questions about number 1 on ellipses? That covered a whole lot. Gotta save this. Okay, now I'll give you about 30 seconds to look things over. It's a big old mess here, but I'll give you about 30 seconds to look things over. All right. Actually, why don't we do this? I'll go ahead and start the 10-minute break. Okay, so return at 8:41. Where am I going to put that? I'll do this here. Okay, so let's return at 8:41 p.m. You can go ahead and stare at this. Right. I'll remember to unmute. Mute now. Okay. Don't get lazy now. Okay, so unmute, mute, and then unmute at the end, and I'll remember to record. I'll see you in 10 minutes, but you can put more questions in chat. In the meantime, look at the beautiful yet messy work over here. All right, so I am going to pause and mute the recording. All right, so we're entering our second third, right? Because I'll take another break. Let's take another break at 9:30, and then I'll be back until 10:30, because I think some people want to stay until then. That's fine. Of course, you're free to leave at any time, but although for class participation, I might remember the people who are here tonight, right? Okay, so now I promised you that I'd go back to now. Any questions about the ellipse before we go on? Any questions about the ellipse? Okay, now a couple of things. So a question in chat. Okay. So I have a question in chat. I'll address this just quickly here before I go on to the factorial one. A question about row and column vectors. Okay, so someone's just having a quick question. So let's say that you have a like a. We'll do this. Let's say that you have a row vector like this, 1, 2, 3, or a column vector like this, 1, 2, 3. You can interpret this as also as a 1/3 matrix here, this row vector. You can interpret this column vector as a 3/1 matrix. All right. Now, in what sense can they have direction? Well, at least here we have 3 space, right? Okay, here's the positive x-axis pointing at you. Here's the y-axis here. Here's the z-axis here. The y-z axis would be like the whiteboard, right? And the positive x-axis points out at you like a 3D movie. I have a really hard time drawing 3-dimensional figures because I know this really messes me up. But basically, this could correspond to a position vector, right? So it's hard to draw these things, right? So yeah, it's a position vector. Maybe start at the origin, okay? And I claim to you this is going through octant 1, where everything's positive. Now, as a student, you might go, well, how do I know? I don't know where the heck that thing's pointing. Yeah, you lose a lot in the translation from 3D to 2D. But in principle, you can think of these as like position vector representations in 3 space. Now, if you have something like this, 1, 2, 3, 4, then I don't think even the late Stephen Hawking could have done that, because you have to envision things in 4 dimensions. Maybe that's a time variable. right? So you have this thing moving in time. Kind of creepy. All right, so those are just my comments about that. And I can come back to this later. Yeah, because the student was asking, well, how can we kind of think of these thin or these thin or squat matrices as vectors, and what do they mean? Yeah, they have geometric interpretation up to 3D, but past 3D, you got to move things through time, I guess, or something. It's hard to visualize. Although I showed you that tesseract, right? When we were talking about the binomial theorem, a plus b all to the fourth, that tesseract is like taking a Rubik's cube and moving it or watching it over time. All right. Okay, now let's go back to when I was promising before, which was I was going to go back to that factorial one, right? 8D, because I told you to work out. We went over 8C, right? Let's do 8D. So if the ellipse wasn't catching your attention, we can go back to 8D now, right? You're working on 8D. We can go back to 8D. All right. 9-1. Yeah, so we're going back to 9-1. Yeah. Okay. So I'll do this in purple. I'm trying to avoid red. Let's do purple. Yeah, because I want red for cancellation. Okay, let's do that in purple. Okay, I am recording. Yes, yes. Okay. All right. Note here. Okay, so we're going back to D. All right, so this is okay. All right. Okay, new problem, purple. (9.18D). Simplify this guy here. Okay, so and I will write this here. 3n minus 2 all factorial over. Even this one accept it. There we go. Over 3n plus 3 all factorial. Question: which is the bigger factorial? That's a good question to ask. Which is the bigger factorial? Assuming n is a nice positive integer, at least 2, which is the greater factorial? It's the one in the denominator, the bottom. All right, so let's start expanding it. Let's unravel it until we get his twin over here. All right. Again, I could probably use it for my equal signs also, but okay. Let's start by unraveling the bottom. Okay, first we have 3n plus 3. Keep counting down. Keep subtracting 1. I'm going to have to expand this. All right, keep subtracting 1. Count down. 3n plus 2. What's 1 off of that? 3n plus 1. What's that? Minus 1? 3n. Let's keep going. I don't see a twin yet. Let's keep going. Who's next? Subtract 1. We have 3n minus 1. And now subtract 1 again. We have 3n minus 2. And then you go, wait a minute. 3n minus 2 and then dot, 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 1. Let's assume n is big enough, right? So you have all these dot, dot, dot times 1. All right. 3n minus 1, sorry, 3n minus 2, all factorial, because we're going to get all the guys up from here down to 1. Multiply together. We have the twin up here. What happens? Massive cancellation. That divided by that is 1. Let's put a 1 here and a 1 here. And why am I doing that? Because, show this work, by the way. You got to show the work. All right, so in the bottom, who's left? We have 3n plus 3. And you don't have to distribute. That's a lot of tedious work. You don't have to distribute. In fact, I think I said here, yeah, do not multiply out. Do not multiply out. Don't bother distributing down here. It's too much. 3n plus 2. Next. 3n plus 1, next. 3n, next. 3n minus 1. Am I done? Am I done? Is that my answer? Remember, we don't want to distribute, but is that my answer? Thank you. 1 over all that. Don't forget the 1 over, all right? Don't forget you have a 1 as a survivor up there. Okay, it's a fraction. Okay. So this will be your answer. Of course, you have the right to multiply this out, but that would be a waste of time. And you have the right to reorder this. I mean, if for some reason you want to put him first, that's fine. But, I don't care what order you put these 5 factors in. But this is pretty much your answer. Maybe reordering these factors. Aside from that, there's no other reasonable answer. No, unfortunately, plugging in a value is not sufficient work. It might be worth some partial credit, but the thing is, you want to make a general argument. So if you plug in like n equals 2 or something, that can help you thinking about what to do, but that's only as a motivator. You do need to show me your work in terms of n. Okay, but you're not wasting your time because what you did with a number, that helps motivate what we did here. So you weren't wasting your time. It's always good to experiment. And very often with these things, with matrices, mathematicians plug in some numbers, they experiment. That's okay. All right, but do show me this work in n also. All right, those are the 2 factorial problems, okay, which I knew would be brought up. 8C, 8D, 8B's in the video, okay? That's a simpler version in a way. And A, this is from the factorial definition. To get the next factorial, take the current factorial and multiply the new number. So for example, basically, if you have 3 factorial and you multiply in the 4, you get 4 factorial. Okay, so this is an example of that where n equals 3. Right? Again, going to the point here, if you plug in numbers, then a point that students make with me privately, if you plug in numbers, that can be helpful. All right. Any questions, by the way? Again, things in videos, especially desirable as solutions. That means that I can point to the video when I offer solutions, right? You notice I've been doing that. That's convenient for me and for you in some ways. It's nice to have these video solutions as things I tend to grade, right? Okay. Questions. There were other questions. Okay, now it's an Easter egg hunt. There's still the induction one we might do again. Okay, so the next one I see, 9.117G, I think, yeah, that's a pretty recent one. I think that's the only remaining one so far. So let me go back to that one. 9.117G, that's the one where, yes, you're being conscientious students. You want to know why these things work. Very good. Because yes, I'll accept answer only, but I would like my students to understand why these things work. So very good. All right, and I could grade some of these. So that you at least know that you're getting used to these patterns, right? Okay, and there's a question about 17G, but I can cover others as well. Okay, so F I did in a video. Okay, I did 17F in a video, 9117F. I did that in a video. Yeah, that was one of the later ones. That was near the end on the Tuesday video. F, 17F. The students here is asking about G. All right, which is kind of related in that there are a couple of ways you can approach G. So I'm gonna do this in blue. All right, I need some more. Need another whiteboard here. Another one. Okay, yeah. So this is one about row matrices and 3D. Okay, that was a good comment. Okay, I need a new whiteboard. There we go. All right. So that up there was G. 9.1, 17G. That's 18, so that's 17. All right. All right. 9.1, 17G. And I'll also label this. All right. Two ways of looking at this. So you see an alternating sequence here, right? So I think that we're going to need, I'll do this in green. We're going to need a sign alternator, and we're going to need the absolute value. I'll leave that in blue. That's fine. Okay. Now the sign alternator, again, going to green. That typically takes on the form -1 all to an exponent. Let's start with n. And it turns out that here, n alone will work. Because remember, in our pre-calculus class, we're starting with n equals 1, right? In pre-calc, in our class, math 141, we start with n equals 1. In pre-calculus, math 150, well, actually, in calculus 2, in math 151, calculus 2, when you come back to the sequence series stuff, you often start with n equals 0. Right, that's a warning. But in our pre-calc class, we start with n equals 1. And -1 all to the first, that's a -1. That's good. We start with a negative. All right. So the pattern goes negative and then positive, negative, positive, negative, positive, negative, positive. All right. We do want the sign alternator. Now in F, and I got confused at first when I did F, you actually want to nudge it. So for F, because you start with a positive, and in this class we start with n equals 1, in F, you want like an n plus 1 or an n minus 1 up there. You want to nudge it so you have a different parity from the index, 1, 2, 3, and so forth. But in G, we start with a negative number, and in pre-calc, we start with n equals 1. This is the appropriate sign alternator. If you want, you could do n plus 2, n minus 2, and so forth, but why do that? Now, for the absolute value part, 2, 4, 8, 16, 32. Hey, those sound like powers of 2, right? I hope you recognize those are powers of 2. 2 to the n. So bottom line, we can say that a sub n is -1 to the n times 2 to the n. The general nth term, where n is a positive integer, can be given by this sign alternator, -1 all to the n, times the absolute value, 2 to the n. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. In fact, I'll write that down, right? For your experimentation, 2 to the first is 2. That's the absolute value of the first term. 2 to the second is 4. That's the absolute value of the second term. 2 to the third is 8. That's the absolute value of the third term. And then 16, and then 32, and so forth. On a final, I would have accepted this, but do recognize that as a basic algebra step, remember you have an algebra rule. Here's the related algebra rule. X to the n times y to the n. How can you rewrite that? You can combine these. It's the nth power of xy. X to the n times y to the n is the product xy all to the n. Similarly, by that reasoning, look at this. How can you rewrite this? You can rewrite this as, well, -1 times 2 is -2. You have the same exponent. I'll accept either. A sub n is -2 all to the n. So that's one way of approaching G. That was the intended way for you to approach G. Now, later on, after studying section 9.3, now, hopefully, you did this homework before you did 9.3. This was meant to be motivation. But let's say you did this homework after 9.3. Then you have the luxury of using the formulas for 9.3. Okay, so I want to show you another way of doing this. Using the methods from section 9.3. Which was a bit naughty in the sense that you should have done your 9.1 homework before we did 9.3. So naughty, naughty. But hey, let's be practical. On the final exam, I couldn't tell the difference anyway. So on a final exam, you know, hopefully, 9.1 and 9.3. So what if you had used the methods from 9.3? Look at the sequence. There's a common what? It just so happens that in this sequence, there is a common ratio. What is it? What is the number that we multiply by to get each successive term? It is -2. -2 times -2 is +4. +4 times -2 is -8. -8 times -2 is 16. 16 times -16 times -2 is -32. R is a common ratio. Hey, what's the initial term? It's also -2. It's the same number. That's a little confusing. There we go. All right. The initial term is also -2. So A, or A sub 1 if you wish, A or A sub 1 if you wish, is equal to -2 also. All right. So I'll go to blue again. Go to blue. Okay. So what is the formula? Okay, I'm going to type this in blue. What is the formula for the nth general term of a geometric either sequence or series? Because I'm talking about the terms of a sequence or a series. All right. So the formula we use for geometric a sub n, the nth general term, is given by a sub 1, or just a, times r to the n minus 1. What's the initial term? It is -2. Hey, the common ratio, that's also -2. There we go. All right. And I guess on a final exam, I would have accepted that, but this is very readily simplified, even more so than before. How come that's an arrow? Okay, wait, hold on a second. All right. All right. I'm having trouble clicking off on stuff. Wait, hold a second. There. Okay, I don't know what that is. I don't know what that is. Okay. All right. So anyway, we have -2 all to the first, all right, and then -2 all to the n minus 1. Okay. So in general, if you had -2 all to the x, -2 all to the y, this is -2 all to the xy. All right. Over here, when you multiply powers of -2, you wait. What am I doing here? You add the exponents. Duh. You add the exponents. Losing it. All right. When you multiply powers of -2, you add the exponents. All right. 1 plus n minus 1 is n. All right. Just like before. All right. And of course, these are equivalent, right? These are all equivalent. These two are exactly the same. A sub n is -2 all to the n. Basically, these are the powers of -2, starting with -2 itself. -2 all to the first, -2 all to the second, -2 all to the third, and so forth. All right, two ways of approaching it. Either by decomposing this into a sign alternator times the absolute value. You recognize those are powers of 2. Or you might recognize, if you did 9.3 before this, if you studied 9.3 before this, these are the terms of a geometric sequence, which can be modeled like so. Okay, that was more programmatic. All right. Any questions? Any questions? I think the only remaining one was the induction one, 9.4 number 1. I think that was the only remaining one. Is that correct? So aside from induction, are there any more questions aside from induction? Are there any more questions aside from induction? Okay, no, I want to go back to the induction one though. Okay, and yes, thank you. Yes, I know some of you have to leave. Thank you. Yes. Uh, and now I'm going to do this. So I know a lot of people have questions about induction. All right. So here's what I'm going to do. I actually did this on Tuesday with another student. So what I'm going to do is I'm going to pause the recording and I want to play for you the Khan Academy video on induction, which is narrated by Salman Khan. Now I'm going to keep the chat on. So if you want to pause or you want me to rewind something, I can do that. I know you can do that on your own, right? But also I can provide commentary and I can help explain things for you. So what I'm going to do now is I'm going to pause recording and I'm going to show for you the Salman Khan video. And if you need me to pause, rewind, or comment on something, I'll do that. Okay, so let's do that now. Okay, so at this point, it's 9:18, but I'll go on for up to an hour plus more, so you can still use me to your benefit. Any questions? Any questions? I'll wait a minute in real time, and then we can do a pause. Okay, so when my clock here reaches 9:19:30. Okay, so at this time, are there any questions at this time? Any questions? So at this time, let's do a pause. And for some of you, happy holidays. I see that it's all red and green in the participants list. I wonder if that's on purpose, but happy holidays. But I'm going to come back. So we're approaching 9:20. I'm going to come back at 9:25 p.m. Okay, so okay, if you would like to return at 9:25 p.m. and I'll check on people. And again, I'm willing to go on past that. Now, bear in mind, if there's no one basically around, I may just turn off. Okay, but let me know at 9:25 if you're interested in continuing. Okay, so I'll see you in 5 minutes, perhaps. Otherwise, happy holidays, and don't forget to give me your stuff. Okay, so we're back. We're back. And I'll take any last questions, any last questions or issues. Let's see. Okay, and thank you. Yes, I've enjoyed the class very much. Thank you. Yes, and feel free to keep in touch with me. Certainly, I'll send out the grade reports. So you know, I'll be keeping in touch with you folks because I got to send out 3 grade reports, I guess, right? 4, and then 5, 6, and then 7 to 10 with the ultimate grades. Right. All right. So it's 9:26. I'm willing to go further. Well, right now, just a couple of us left. All right. Any last questions? And thank you. Thank you very much. All right. So we do have, let's see, 9112. All right. So I'll switch this off. Let's see. Oh, did I, okay. I'll turn these off. I've saved these, right? Okay. 9112. Right. Okay. Yeah. Recursive sequences, which often confuses people. Right. Okay. Bring up another blank sheet here. Okay. So go to green. Yeah. Go to green. All right. Okay. So 9.112. Let's see here. All right. Okay, so for 9.1 number 12, so we have these seeds, right? So a sub 1 is 2. I'll refer to these. So a sub 1 is 2, that's the first term. A sub 2 is 3, that's the second term. And then this is saying that, I'll write this out. So we have a sub k plus, well, a sub k plus 2 equals a sub k plus 1 times a sub k, where k, I could have written this as where k is a positive integer. I could have made that a bit more efficient, where k is a positive integer. So this makes sense. All right, given these seeds. So what is this basically saying? Okay, kind of thinking in terms of a family tree. So this is saying that, how should I put it? That you are equal to dad times grandpa, something like that. Or maybe you equals mom times grandma, all right? So to get this term, we take the product of the two previous terms, all right? Using the domino image. So in a way, this corresponds to strong induction, not weak induction, but using the domino image, we need the two previous dominoes to tell us what's going on with this third domino over here. We need dominoes 2 and 3 to tell us what happens with domino number 4, and so forth. All right, so let's go through. A sub 1 is 2. A sub 2 is 3. Those are the given seeds for this recursive sequence. And then for a sub 3, we're saying that a sub 3, we're plugging in k equals 1. So a sub 3, 1 plus 2 is 3. A sub 3 equals a sub 1 plus 1 is 2. That's a sub 2 times a sub 1. A sub 3 equals a sub 2 times a sub 1. That tells us that to get this term, we need to multiply together the two previous terms. A sub 3 is 3 times 2, or vice versa. We get 6. Okay, it's kind of like Fibonacci, except this time we're multiplying, not adding. To get the next term, okay, 3 times 6 is going to give us 18, because to get a sub 4, plug in k equals 2 now, a sub 4 equals a sub 3 times a sub 2. Again, technically this corresponds to k equals 2, that case. A sub 3 is 6. A sub 2 is 3. 6 times 3 is 18. And a sub 5, we go one more. All right, so for a sub 5, I'll go to brown. For a sub 5 here, 6 times 8, is that 108? Yeah, 20 times 6 is 120, minus 12, 108, right? So the first 5 terms, I gave you the first 2, those are the seeds, right? Now we're looking at the 9.1 number 12. Okay, it's 108, yeah. So 2, 3, 6, 18, and 108. We start with the 2 seeds, and it's similar to Fibonacci, except we multiply instead of adding. 2 times 3 is 6, 3 times 6 is 18, 6 times 18 is 108. Or you could do it more brute force. You could appeal to this formula. A sub 3 is a sub 2 times a sub 1, a sub 4 is a sub 3 times a sub 2, a sub 5 is, if I can squeeze this in, a sub 4 times a sub 3. Either way is fine. Either from a formula approach or just conceptually, you multiply the 2 previous terms to get the new term. And you could go on after this in principle. Although I couldn't do it in my head. Okay. Any questions about that? Is there any point that I could clarify there?
It's just it's not really clicking. I don't know how you could carry over, like go A3 or A sub 3 times A sub 2 if the last term was,
So
I don't know how to explain it.
okay, so let's do it more formulaically, which I think might be more accessible to our students. So I'm going to bring back the question. And sometimes the formula is so complicated that you pretty much have to do it using formulas. All right, so let's begin at the outset. So we have A sub 1 equals 2, A sub 2 equals 3. Those are the given seeds. Now, the first one you have to really figure out is A sub 3. All right, so I'm going to rewrite this general form. I'll do that in green. I'll do it in green or turquoise. All right. So here's the general form: A sub k plus 2 equals A sub k plus 1 times A sub k. So strictly speaking, in the case where k equals 1, A sub 1 plus 2 equals A sub 1 plus 1 times A sub 1. So strictly speaking, if you want to substitute 1 for k, we get this. This says that the rules for A sub 3 is A sub 2 times A sub 1. That tells us how to construct the third term, A sub 3, based on the generic recursive formula over here. The new term A sub 3 relies on the previous two terms, A sub 2 and A sub 1, dad and grandpa. Over here, let's apply that idea. A sub 3 is, again, A sub 2 times A sub 1. A sub 2 was 3. A sub 1 was 2. 3 times 2 is 6. That's our third term. Any questions about how we arrived at A sub 3, the third term of this sequence? And by the way, this is neither arithmetic nor geometric. It's a more generic sequence.
Good so far.
Okay, let's do another one. Let's do A sub 4. Okay, and perhaps it is beneficial to repeat with the K notation here. So let's see. I'll do that in purple just to get the colors different. Do it in purple. Okay. So I'm going to repeat the generic formula here, the generic recursive formula. A sub k plus 2 equals A sub k plus 1 times A sub k. Let's now take the case k equals 2, because this applies to all positive integers k. I could have just said that up there. Okay, the case k equals 2. A sub, subbing in 2 for k, 2 plus 2. Equals A sub 2 plus 1 times A sub 2. Simplifying the subscripts or indices, A sub 4 equals A sub 3 times A sub 2. This tells us that to get the fourth term, I don't want to hit the caption, so let me go here. All right. So to get the fourth term, A sub 4, we take A sub 3 times A sub 2. Again, to get the new term, we take its father and multiply by the guy's grandfather. So this term equals the father times the grandfather, or the mother times the grandmother. A sub 4 over here. I'll go back to brown. Yeah. All right. A sub 4 equals, again, A sub 3 times A sub 2. A sub 3 we just found. That was 6. Okay, we're kind of climbing up the ladder where we need the bottom two rungs to get to the third rung. All right, and then the second and third rung to get to the fourth rung. That's what we're doing here. A sub 3 was 6. We're given A sub 2 is 3. And 6 times 3 is 18. That's A sub 4 the fourth term. And then similarly, what is a sub 5? That's going to be what times what? A sub
4, a
4
sub 3.
times a sub 3, and so forth. In principle, you can build up to a sub 6, a sub 7, someday a sub a million. So you have the means of constructing the entire infinite sequence. And in this case here, 18 times 6 is 108. On a final, I would have allowed a scientific calculator because my arithmetic is not that good. Oh, and I may as well show that step to complete the work here. 18 times 6. Although multiplication is commutative, you can multiply in any order, but I am strictly following the order in the recursive formula, and that is 108.
So technically, it looks like it's a as a function of a. Is it?
Oh, you know what? Sequences are functions. So you're right. A sub n is a function of n. Where the domain, function of n, where the domain is z plus. It's not all reals. The domain for this function, and I mentioned this on, I think, the first page of 9.1, which is a long time ago, 1, comma, 2, comma, 3, comma, dot, dot, dot. That's the domain. You know, back in chapter 3 or 2 or whatever, we had domains like the reals, the positive reals. Now, in chapter 9, our domain is going to be a set of integers. It's a discrete domain. It's a discrete domain. And a sub n is a function of n. So it's kind of like f of 1, f of 2, f of 3, f of 4, f of 5, right? But the input values are only allowed to be positive integers. The domain is very restricted to the positive integers. But yes, here you can think of this infinite sequence as a function where the domain is z plus the set of positive integers. So it's a very restricted function. And you would graph this as dots. The GeoGebra applet does that actually. You can graph the thing.
So the domain for these a functions is always positive integers.
I mean, you know, you could start with 7 or 8, or but yeah, in a sequence or series problem, the domain would typically be a set of integers, usually the set of all integers that are greater than or equal to some number. It's not always 1, but it could be all integers that are at least 7, or all integers that are at least 15. There's normally a starting point, right? Kind of like induction, right? There's like a basis step. There's a starting point. There's a first integer where we claim that the formula applies. In this case, it's k equals 1, but in something else, it could be k equals 7. In our stamps problem, it was k equals 6, right? 6 cents was the lowest amount of postage you can get with just 2-cent and 3-cent stamps, where you could induct from there, right? I mean, 4 is 3-cent stamps and 4-cent stamps. You know, you get a 4-cent stamp by just taking a 4-cent stamp, but you can't get 5-cent stamps anywhere. You can't get 5 cents of postage from just 3s and 4s. So 6 worked, and then 7, 8, 9, and then forever. So the basis step here was basically k equals 1, but in other problems, it could be different.
All right, that helps. Thank you.
You're welcome. Yes. A basis step is actually a term from induction, but I'm using that idea here. A sub 1 is 2. That's the first rung on the ladder. And once we get the first 2 rungs, we can then get all the rungs on the ladder. But to start the process, we need 2 seeds, right? We need the first 2 terms, because each successive term depends on the previous 2 terms. So we needed 2 seeds to start this thing. You can see what happens. You can experiment if you had different seeds, right? Like 4 and 7, or if one of these is negative, you could get an alternating sequence. Again, I sent out a GeoGebra link where you can play with various sequences, and it'll give you some sample values and plots. Okay, this plot would be like, if you graph a sub n against n, domain is z plus 1, 2, 3, and so forth. A sub 1 is 2. A sub 2 is 3. A sub 3 is 6. Now this is going to go very rapidly because we're going to go to 18 and 108. So kind of like with factorial, this thing grows very rapidly. In fact, this thing is going to grow probably faster than faster than factorial? Yeah, maybe. With factorial, you just multiply the next integer up. Here, you're multiplying by a product. So yeah, this thing's going to grow very fast. It's probably going to be worse than factorial in the long run. Yeah. Okay, so any follow-ups on this one, or is there another question that you'd like to address?
I think that's it for me. Thank you.
You're welcome. Now, I could do another pause. Would you like to take a look at your homework, and I'll come back in 5 minutes?
Sure.
Okay, so I'll come back at 9:47, and then we'll do a check on things.
Cool. Thank you.
Okay. And some people might be coming back. Who knows? So let's say 9:47. I'll announce it, 9:47. Great. Okay, so I'll pause for now. Okay, and then turn back the volume. All right. Okay, so which question?
6 or 7 on 9.1.
Okay. All right. Now let me turn this off here. Okay. Oh, by the way, let me label this one 9112. 9, 1. And yeah, a lot of people had questions about the recursive one. Okay, so saving that one. All right. Okay, so okay, 916. 6 was
Yeah,
it?
or 7.
6 or 7, right? Yeah, these are the combination ones, and these are ones that always confuse my statistics students. Also, these are like the stats ones, the combination stuff. All right, and both of these are the combinations, the C, right? So let me explain that. I'll get a whiteboard, even though it's a short answer, but I want to explaining it does take some time though. That's often the case with these problems in stats. It's not too long to write, but it's understanding why they work. That's the problem. Okay, so let's purple's fine. Okay. All right. 6. Okay, it's the 9-6 part of 9196. All right. Okay, so whoops. All right, so we're looking at 9196, number 6. And it's a counting problem, which is 9.6 in the old Larson text. Okay, so it's technically 9.6, number 6, but whatever. Okay, so 7 of your friends are sitting in a room. And it's good to have some basic graphics. Okay, so you have your 7 friends. Okay, sitting in the room. You have 2 identical plane tickets that you'll give to 2 of them. All right, so we have these 2 tickets, but we don't distinguish between them. All right, so basically it's almost like an election. It might help to reframe the problem. Imagine 7 students in a classroom and they elect 2 senators to the student senate, right? Then how many ways can we choose 2 out of 7? Well, literally that is 7C2 or 7 choose 2. Okay. And it's 7C2, not 7P2. So it's not 7P2 because these are unordered. We have 2 plane tickets, and it's not like one is better than the other. It's not like one is for first class and the other is for coach. It's not like that. They're just 2 plane tickets that are equally good. All right. You have 2 identical plane tickets that you'll give 2 of your friends in the room. So that's 7 choose 2. Among the 7, how many ways are there to choose 2 distinct people out of the 7 distinct people to give tickets to? So this was meant to be an analog to the card problem, right? How many 5-card hands are there in poker, right? That would be 52 choose 5 or 52 C5. This can normally be computed on a scientific calculator. Like, for example, if you have a TI calculator, for example, you might have to use the PRB button. If you have a TI calculator, you might have to use the PRB probability button. So on calculators, you might enter something like 7 and then the NCR button. There's a button, and then 2 equals or enter. Although, to be honest, I had some old calculators, like very old calculators, 20, 30-year-old calculators, where I never figured out how to figure out combinations. You know. But yeah, on a TI like 30, for example, or 36, you could use 7, go into the probability menu, get the NCR function in there. It's listed there in the menu. 2 equals. And what is that? That's 21. In fact, just like here, we can do it. We can do it with some basic work, actually. Okay, what is this? So I'll erase this over here. These are the poker hands, 2.6 million or so. Okay, so what's the formula we use for this? Equals 7 factorial. If you want to line up all your friends in order, okay, and then so it's like you have 7 friends, you put them all in order. So friend number 1, 2, okay. However you want to do it, by how much you like them, age, height, whatever. All right. However you choose to give the tickets to your friends by whatever criterion. Okay. And then it could even be how much you favor them. That's kind of rude, but ordering them by your best friend to your least favorite friend, that's a little rude. But and the idea is that you have this dividing line between these 2 friends who get the tickets and these 5 friends who don't. I'm assuming the tickets are to someplace desirable, like Paris. Okay, not someone's basement. All right. Okay, but you don't care about the order between the 2 tickets. You don't care who gets which ticket. You divide by 2 factorial, or 2, right? And you certainly don't care about the order among the 5 friends who don't get tickets. So you divide by 5 factorial. That comes from the formula for NCR. How do you simplify this? 7 times 6 times, lo and behold, 5 times 4 times 3 times 2 times 1. Do you know another name for that? 5 times 4 times 3 times 2 times 1. That's also known as 5
factorial.
factorial. The point being, 2 factorial is 2. That's very nice. Now, 5 factorial is 120, but we don't have to worry about that because it cancels out with itself. Whatever 5 factorial is, it's 120, but who cares? I shouldn't say that, but we don't care here. The 120 divides by itself. We know this. Basically, 7 times 3 is 21. And it's an interesting result from number theory that when you work out this kind of a factorial fraction, you do get an integer. Okay, these combination numbers will always be integers, right? It does make sense because there's a combinatorial interpretation. They're going to be integers. So 21 ways. There are 21 ways. I'm not going to grade on the unit. There are 21 ways of doing this. You have 7 friends. There are 21 ways to give a pair of tickets to 2 of your 7 friends where you don't care which ticket's which. Now you don't have to show even this work here because I'm assuming that students know how to get this on their calculators. Though I admit I've had calculators where I didn't know how to do this on my calculator, but if a student can find this on the calculator, 7 NCR 2 equals something like that, you get 21. However, for work, I would want to see, so what would be work here? One of these notations. So for work, you should tell me that it's either 7C2 or 7 choose 2, same thing. But for your work, I do want to see one of these notations. That's in the online answers, 21.
And what if it were P2?
Now that's if one of these tickets were first class and one of these tickets were coach. Then we care about the order. All right, so 7P2, that's like 1 ticket. I'll do this in blue. That's if one of the tickets were first class and the other's coach. So it matters, right? So this is before you decide, which is your favorite friend, but you consider your 7 friends. And before you think about, okay, who's my favorite, who's my next favorite, okay, well, we have 2 different tickets. Whoever your favorite friend is, that person's going to get the first class ticket. Your second favorite friend's going to get the coach ticket. And the other 5 stay home. All right. Well, here's one way to look at it, right? 7 friends. How many ways are there to give the first class ticket? 7 ways. 7 ways. 7 ways to pick your favorite friend. times, because you could use different criteria for who your favorite friend is. And then once you know who your best friend is, how many ways to pick your second best friend? 6. Because the first person cannot get both the tickets, right? So our sample here has to be without replacement. We're not allowed to use the same person twice. So 7 times 6 is 42. It's as simple as that, really. Okay, you can think of a tree, right? A tree for the first class ticket, and then more branches for the second class ticket. 7 of these for each of these branches, 6 of these. 7 times 6, there are 42 paths you could take, where you could assign the first class ticket and the coach ticket. The way that this is normally done with a formula, I'll grab a. The formula is easier actually than for NCR. So the NPR formula would work like this.
You're missing the 2 factorial on the bottom, right?
That's right. Okay, so 7p2, you still consider ordering all 7 friends, okay? But you don't care about the order about the 5 friends who stay home, okay? Before we divided by 2 because before we didn't care which ticket was which. Now we do. Now you don't divide by 2. Do you agree that? In fact, we know this is going to be 42, right? Because it's going to be twice 21. So basically, there are 21 ways to assign 2 generic tickets to your 7 friends, to 2 of your 7 friends. Now, if you care which ticket is which, there are twice as many possibilities. There are 42 ways, because among these 21 ways, there are 2 different ways to decide which friend gets which ticket, the first class or the coach. So that kind of makes sense. 7C2 is 21. 7P2 is 42. That kind of explains how in a lottery, right, which would be a harder lottery to win, if it matters what order the balls come out in, or if it doesn't matter. It matters that it's harder to win if you have if it matters which order the balls come in. Then the probability of winning that is 1 over a bigger number, right? Because there are more possibilities if you care about the order, if you care which the first ball is, which the second ball is, and so forth.
Makes sense.
Very good. Yes, and you're going deep into stats. Bear in mind that on the 2 homework problems, on both 6 and 7, it's just the NCR case. But you're good enough to ask me, well, what about NPR? You're curious. So that was the explanation for NPR, where you care about the order, or you distinguish among the chosen items. In both 6 and 7, I'll explain 7. 7. Okay, I'll save this and I'll get a new one. Okay, let's address 7. That's also NCR. Because these were the ones that applied to the binomial theorem. The NPR didn't care about as much because the NCR ones were the ones that applied to the binomial theorem. All right, but anyway, 7 is also NCR. Let's explain why. Let's put that in brown. All right, so this is a 9.6 really, number 7. All right, so this is 9.1, 9.6, number 7. But again, in the Larson book, 9.6 was counting. I just moved that up to the sequence series stuff up here. All right, so 10 basketball players. So we have this room of 10 basketball players. They're not ordered right now. Not yet. Okay. They're to be divided into 2 teams of 5 people each. All right. But here's the thing. So they're going to split 5 and 5, right? But you agree that once we know the composition of one team, well, we know who's on the other team, right? So whoever's picked for one team, we know that the remaining players are going to go on the other team, right? So we may as well just focus on the first team. So if we have team A and team 1, we just focus on like team A, for example, right? And then everyone else is on team 1. Well, again, we have 10 distinct items here, the 10 players, no clones or twins here. All right. How many ways are there to pick 5 people out of 10? All right. To form our team A. That's going to be 10C5, or same thing, 10 choose 5. And then the remaining players go on team 1. Now on your calculator, hopefully you can find the NCR button on your calculator or use the probability menu for a TI calculator. It turns out to be what? What is 10 choose 5? It's 252. Now you don't have to show me the factorial work, but it is a good exercise. So let's do it. The formula goes 10 factorial over 5 factorial, 5 factorial. Again, you don't have to show this work because I assume that you can use your calculator directly for this NCR. Let's try it. Okay. So 10 factorial is 10. How do you want to write this out? How should I write out 10 factorial? 10 times? Who's next? 9 times 8, 7 times 6, and then what?
5 factorial.
Yes, because 5 times 4 times 3 times 2 times 1, why waste our time? That's 5 factorial. We multiply the integers from 5 down to 1. All right, let's see here. Fraction bar, don't forget the fraction bar. Now why we start with a 5 factorial? Okay, well, it's going to cancel out with one of these 5 factorials over here. Okay. Okay. All right. So go to red for the cancellation. Whatever 5 factorial is, it divided by itself is 1. But it's good to know what it is anyway, because it turns out that we have a 5 factorial here also. That turns out to be 120. Turns out to be 120. The arithmetic is a bit harder, and it's not as obvious that it's going to be an integer, but according to number theory, this will always be an integer. So if you work this out, right, you can use like a $2 calculator to work this out, you will get 252. In fact, if you want to see some speed arithmetic, the arithmetic's not too bad. Okay, 10 times 9, oops, times.
Oh, you don't have to if you don't want to.
We're just showing how, just quickly, right? 10 divided by 10 is 1. 120 divided by 10 is 12. Take the 6. 6 divided by 6 is 1. 12 divided by 6 is 2. So a bunch of cancellations. 8 divided by 2 is 4. 8 divided by 2 is 4. 2 divided by 2 is 1. That's an integer up there. 9 times 4 times 7. 252. Right. All right. It's cool to see that. Yeah. It's not convincing that's an integer, but it does turn out to be integer. Number theory guarantees that. Okay, so again, these were both NCR problems. I don't think I ever tested on NPR. Although do note that as a special case, it's true that NPN is n factorial, and of course, I used to test on n factorial. That's if you have n people, like n runners, and you do care about the order of all n runners. They all get a different color medal. N factorial. But more generically, I didn't test before an NPR, not the partial permutations, only full permutations. Okay, any follow-ups on these, or is there another question?
I think I'm good. Thank you.
All right. Okay, now once again, if you wish, I could pause for another 5 minutes, or what do you think? Do you think you're good for the day, or I could pause for 5 minutes? I'm awake.
I think I'm good for the day.
You're good? Okay. So again, thank you for everything. Thank you to you and the whole class, and happy holidays.
Yeah, wow. Thank you. Happy holidays, man.
Yes, that's it. So thank you for a great class, everyone. And that's the last piece of video, I guess. Unless there's some sort of office hour, I guess I could post that on Monday. That's possible, right? Sunday or Monday. But otherwise, I'll sign off. Happy holidays, and I wish you all a much better 2021 than 2020. Okay. Thank you all. Good luck.
Thank you. Take care, man.
Take care. Thank you.